Black holes, among the most bewildering and exceptional phenomena in the universe, are still a subject of remarkable analysis and captivation for astronomers and theoretical scientists. Similar to these astronomical objects characterized by the size of their gravitational strength and the complete absence of emitted light, they signify a threshold beyond which established principles of physical science cease to function. Originally hypothesized by Albert Einstein in 1916 as a result of his general theory of relativity, black holes remained purely hypothetical until modern technology enabled their indirect observation during the 20th century. A pivotal moment emerged in the 1960s when researchers examining the Cygnus constellation inadvertently identified a peculiar stellar body, a radiant blue star releasing intense X-ray radiation. This star, locked in orbit with an unseen partner, resisted conventional explanations until it was determined to be gravitationally bound to a colossal black hole known as Cygnus X1. The detection of Cygnus X1 offered tangible evidence of the existence of black holes and ushered in a transformative phase of research into these cosmic mysteries. Located about 6,000 light-years away from our planet, Cygnus X1 possesses astonishing traits. It is extraordinarily dense and generates a gravitational influence so powerful that even photons cannot escape. This hallmark feature led to the designation black hole, effectively capturing the essence of these enigmatic structures. Subsequent investigations have identified an assortment of black holes dispersed across the cosmos, with projections indicating that our Milky Way galaxy alone could contain over 100 million such objects. Although their elusive properties complicate direct observation, numerous possible examples from our galaxy, ranging from stellar mass black holes, originating from the collapsed cores of enormous stars, to supermassive black holes residing in galactic centers, have been identified by astronomers. The gravitational pull of black holes affects more than just nearby space, influencing the development of universal structures and the destiny of adjacent matter. Matter that drifts too close to a black hole meets a fate governed by its unyielding gravitational power. It is gradually drawn toward the event horizon, an ultimate barrier where it undergoes extreme gravitational stretching and is ultimately absorbed by the singularity. Centered on this dramatic procedure, called spaghettification, is the intense result of a black hole's gravitational dominance. As an object nears the event horizon, the difference in gravitational pull across its structure becomes so extreme that it is elongated and deformed into a fine strand that looks like spaghetti. The gravitational forces surpass the cohesive bonds holding the object together, tearing it apart and assembling it into a stream of particles that ultimately integrate with the singularity. Though black holes offer a remarkable opportunity for examining the extremes of physics, they remain cloaked in mystery. The effort to decode their nature persists, fueled by a longing to comprehend the core aspects of space-time and gravitational mechanics. Amid the vast expanse of the cosmos, black holes stand as quiet guardians, inviting humankind to delve deeper into the unexplored and broaden the frontiers of understanding. Despite the enormous remoteness from the nearest black hole, estimated to be around 1,500 light-years, questions and apprehensions regarding their possible effects persist. In 2021, scientists made a groundbreaking stride by obtaining the first definitive image of a particular black hole, the one at the heart of galaxy M87. This extraordinary feat delivered pivotal knowledge about black holes and their elusive form that was captured in the images. These images show that black holes consist of intricate layers, confronting the long-standing notion of them being isolated voids of absolute emptiness. Through detailed study and image compilation, researchers distinguished three specific layers within a black hole. The outermost is the event horizon, a vital boundary indicating the limit beyond which return is impossible. Once something passes this threshold, gravitational acceleration becomes unstoppable, sealing its plunge into the depths of the black hole. So, what lies inside a black hole? Progressing inward, the second layer is formed by the photon sphere, a zone where light orbits the black hole endlessly. Any photons entering this area are dominated by gravitational influence and remain eternally confined within the black hole's grasp. At the very center exists the singularity, the third and final zone, where physical laws disintegrate. The familiar principles that govern space and matter collapse, ushering scientists into a domain of vast ambiguity and theoretical conjecture. The inherent intricacy and diversity of black holes pose major hurdles for scientific interpretation, although many share a typical three-layer model. Every black hole has distinctive properties and actions that avoid conventional classification. Therefore, classical scientific methodologies often fall short when exploring these immense cosmic phenomena, demanding inventive and novel techniques for bringing their truths to light, since direct analysis is not feasible due to the overwhelming gravitational constraints. Indirect monitoring remains the main approach for studying black holes. Any mission attempting to deploy instruments into a black hole would face inevitable obliteration by the extreme gravitational environment. Still, researchers maintain their pursuit of understanding these astronomical titans. Numerous hypotheses, from stellar collapse to dynamic cosmic evolution, provide captivating insights into their origins and nature. NASA's observations of the central region of M87 uncovered convincing indications of a supermassive impact caused by a massive black hole. Despite the numerous difficulties, the drive for discovery moves forward, powered by the innate human urge to explore and explain. The enduring commitment to scientific discovery holds promise for unveiling the universe's darkest secrets. Roy Kerr's revolutionary findings in 1963 provided a paradigm-shifting perspective on black holes by proposing a model of rotating black holes that challenged accepted doctrines. A cornerstone of Kerr's theory was the ergosphere, a surrounding region where opposing forces neutralize total gravitational collapse, preventing the situation from falling further inward. This unusual area exhibited remarkable deviations from standard physics, pointing to the deep puzzles buried within black holes. However, possibly the most captivating result of the hypothesis proposed by Kerr was an Einstein-Rosen bridge, or wormhole, a speculative construct that could link distant regions of space or even parallel realities. The wormhole concept emerges from the sophisticated relationship between reality and the principles defined by general relativity. In this vision, reality is woven into a tapestry with 4 dimensions, called spacetime, which is warped by mass, creating gravitational effects. We observe wormholes are, in essence, shortcuts through this vast fabric, potentially joining widely separated locations in space and enabling rapid transit across the cosmos. Still, their structural integrity and usability remain contentious among physicists, while wormholes open up thrilling prospects for interstellar voyages and temporal experimentation. Serious barriers and theoretical inconsistencies dampen these hopeful visions. Their fragile nature, along with challenges from quantum theory and radiation, casts doubt on their functionality as transport mechanisms. Furthermore, general relativity sets hard limits on movement speeds through spacetime, implying that even if wormholes were stable, they might prohibit travel faster than light. Fundamental to science fiction. Despite the fact that wormholes persist to inspire scientific inquiry, their notion, named after their foundational theorists, embodies the exciting concept of universal passageways and alternate dimensions, sparking humanity's imagination about the broader cosmos and its infinite potential. The ambition to forge a single, unified explanation that bridges the gap between gravitational theory and quantum mechanics has led scientists toward a theory of everything, a total model that encompasses all elementary forces and particles. At the forefront is the mission's head physicist M. Theory, whose pioneering research has advanced superstring theory. This theory marks a profound shift from conventional paradigms by proposing that elementary particles are not tiny dots, but Minute, vibrating strings. These strings, similar to those on musical instruments, vibrate at unique frequencies, generating all known matter and forces. In this view, the universe resembles a grand composition, with each particle symbolizing a specific tone of these elemental strings. Superstring theory may also illuminate some of the most puzzling features of black holes, wormholes, and other exotic elements within Einstein's gravity equations. The oscillation of strings through spacetime contributes to the emergence of singularities and topological oddities. Despite its beauty, superstring theory is extremely complicated and requires the existence of extra dimensions beyond the familiar 3 spatial and 1 temporal dimension. These hidden dimensions, not directly observable, challenge human perception. To illustrate their elusive nature, analogies like fish living on a 2-dimensional surface demonstrate how beings in a limited dimension might be unaware of those in higher spatial planes. Hidden dimensions are believed to be compactified or curled up, making them undetectable in daily life, yet they profoundly affect physical phenomena. Though their exact character remains undetermined, their theoretical presence offers valuable explanations for the universe's strange behaviors. Additionally, mathematics behind superstring theory has sparked a revival in theoretical physics, revealing links between abstract math and the tangible universe. Indeed, the drive to discover a theory of everything has unified various scientific fields, highlighting the deep relationship between numbers and natural laws. However, superstring theory still awaits experimental support, as its predictions are hard to test due to the invisibility of higher dimensions. Even so, the bold vision of superstring theory continues to enthrall scholars and dreamers, urging humankind to pursue intellectual growth and comprehension of the cosmos. As we progress through modern physics, we stand guided by this brilliant theory on the cusp of greater understanding and awareness. Decoding the puzzle of quantum black holes has long baffled researchers and remains one of the greatest puzzles in physics. Despite countless attempts to resolve this conundrum, a complete answer has proven to be elusive. Edward Witten, from the Institute for Advanced Study at Princeton, famously called superstring theory 21st century physics that accidentally arrived in the 20th century. But its relatively recent developments have reinvigorated hope. Multiple teams have independently unveiled major progress, indicating that, indeed, string theory may provide a comprehensive solution. Though currently limited to simplified 2-dimensional models instead of the 10-dimensional structure normally proposed by string theory. Although this marks meaningful advancement, a full resolution is still pending, as the intricacies of the issue present major obstacles. The ongoing journey toward a unifying theory calls upon us to explore the farthest reaches of the cosmos, where the line between fact and theory blurs and profound revelations await. The study of black holes holds deep importance for our comprehension of the universe, challenging core beliefs about reality and provoking philosophical reflection. The interaction between black holes and other astronomical phenomena, such as neutron stars and gamma ray bursts, unveils the delicate mechanisms shaping the structure of the cosmos. These celestial collisions and energetic displays are not merely random. They serve as insightful markers of cosmic behavior that illustrate how gravity and energy interact on scales far beyond human experience. Black holes, once thought to be theoretical oddities, now play a central role in explaining the dynamics of galaxies, star formation, and even the evolution of the universe itself. As scientific instruments grow more advanced, from gravitational wave detectors to space-based telescopes, our ability to monitor and study these enigmatic objects improves. Discoveries like the detection of gravitational space-time waves caused by black hole mergers have validated long-standing predictions and introduced a brand new horizon for astrophysical exploration. At the intersection of observation and theory, lies the continued attempt to merge Einstein's general relativity with quantum mechanics, a challenge that black holes uniquely embody. These cosmic singularities present conditions where both sets of rules must apply, yet currently conflict, forcing scientists to rethink the foundations of both disciplines. Black holes, wormholes, and the space-time fabric they manipulate may eventually provide the key to unlocking a more comprehensive model of reality, one that seamlessly includes quantum field theory and gravity. Until then, they remain both puzzles and promises, prompting continual inquiry and inspiring a new generation of thinkers. From Einstein to Hawking, from string theorists to observational astronomers, the story of black holes reflects the ever-evolving sticked with conversion, ever-evolving quest to understand our place in the universe, with every equation, simulation, and image captured. We come closer to unraveling not just the secrets of these cosmic powerhouses, but also the fundamental nature of existence itself.